There's a cat meowing at the door. Never mind. Okay. Okay, here we go. This is a whole bunch of things you really ought to know about. You really need to know about exponentials. And next time we'll get into their inverses called logarithms. This is very useful stuff, especially if you're ever going to, let's say, take out a loan, say, or bank money or something like that. So here we go. An exponential function is in the form f of x equals a power x. A is called the base, x is called the exponent. For example, 2 to the x. 2 to the 0 equals 1, 2 to the 1 is 2, 2 to the second is 4, 2 to the third is 8, 2 to the negative 1 is a half, 2 to the negative 2 is a quarter, 2 to the negative 3 is 1/8. Now you plot all these points from here, you get this shape. Here it is, a negative 3 by an eighth, negative 2 by a quarter, negative 1 by a half, 0 by 1, 2 by 1 by 2, 2 by 4, and so on. It starts out very small, and then explodes upwards like that. Now, if a is bigger than 1, then it starts small and ends big. It's called an exponential explosion. If a is between 0 and 1, then it starts big and ends small. This is called exponential decay. 1 to a power x is always equal to 1, so 1 to the x function is just flat like that. A to the 0 is always 1, so these all go through 0 by 1. Let's see. Here's 3 to the x, starts small, ends big. Here's 2 to the x, starts small, ends big. 1.5 to the x, small to big. Now, 1 over a to the x is the same as a to the negative x. So here's a graph of 3 to the x, and here's a graph of 1/3 to the x, which looks like the 3 to the x graph flipped left for right. The half to the x graph is the 2 to the x graph flipped left for right. The 2/3 to the x graph is the 3/2 to the x graph flipped left for right. So here's this shape. I call this the peacock's tail. So a bigger than 1, it starts small, grows big. A between 0 and 1, it starts big, and small goes to 0 by 1. Okay, so here's one use of the exponential. Compound interest. If P is the initial value, or what's called the present value of an account, and A is the final value or future value of that account, and R is the annual interest rate, and K is how many times it compounds per year, and T is times in years, then A equals P times this, which is an exponential, 1 plus R to the, over K to the power KT. This is an exponential in T. Generally starts small, ends big. So for example, a graph of 5 to the x, well, 5 is bigger than 1, so it starts small, ends big. A quarter of the x, well, it's between 0 and 1, so it starts big and small. Here's 3 to the x minus 2. You have a 3 to the x graph, starts small, ends big. We lower it by 2 units because of the minus 2. So here's a left asymptote of -2. At 0, it's at 3 minus 2, which is 1. So it starts at -2, goes through 1, -1, then zips off to positive infinity. Graph of -2 to the x, it's the 2 to the x graph flipped up or down. Now, here's a compound interest problem. $10,000 is invested at an 8% rate for in a account that compounds 4 times per year. And after 10 years, what's the later amount? Here we go. A equals P times 1 over plus R over K to the KT. P is $10,000, 1 plus R is 0.08 over K is 4, the power KT, which is 4 times 10. So that's 10,000 times 1.02 to the 40, which, run your calculator because it's the easiest way to do this, is about $22,080.40. More than doubling. In 10 years, 8% will more than double. Something worth knowing. How much more interest would $10,000 earn in 5 years, compounded quarterly, than at 5% interest, at 5.5% interest, than at 5% interest? Okay, at 5% interest, the amount is 10,000 times 1 plus 0.05 over 4 to the 4 times 5. At 5.5, the amount is 10,000 times 1 plus 0.055 over 4 to the 4 times 5. You work it out, it's 1282.04 versus 1314.07. This is bigger than that by $32.03. So that 0.5% interest is worth $32 more dollars in 5 years. Okay, we're done with this.